guys. So in this video, we're going to go over specific heat capacity. So in the previous video, we just looked at how to change the internal energy of a substance. And now we're going to go over how can we calculate the thermal equilibrium temperature reached when we drop maybe ice into a bucket of water. And thermal equilibrium is that final temperature reached because it comes into equilibrium with its surroundings. For example, if you had a can of Coke and you brought it out of your fridge, you know the can of Coke is really cold, but what's going to happen is it becomes into thermal equilibrium with its surroundings. So eventually the temperature of that can of Coke is going to increase until it comes in equilibrium temperature with its surroundings. So how do we do this? We look at specific heat capacity. So this is the equation we use to calculate specific heat capacity in both Edexcel and OCR. However, in AQA, because it likes to be different, in AQA they use the letter Q here to represent energy. Okay, but let's just use E for energy because it makes more sense, because AQA uses E for energy everywhere else apart from this topic. Okay, and what this stands for, we know that triangle always stands for delta, which is change in physics because we're lazy, and this stands for a temperature. So if we want to define what specific heat capacity is, it's the energy, E-N-E-R-G-Y, just take it and spell, energy to change, or energy to change the temperature of 1 kilogram, because it's got mass in it. So energy to change temperature of 1 kilogram of substance by 1 Kelvin without a change in state. Okay, you need to write all of that for your definition of what specific heat capacity is. Okay, you might think, what's Kelvin? Maybe you've not seen Kelvin before. Kelvin is our SI base unit, that international system of unit for temperature. Okay, we use Kelvin as the base unit because 0 Kelvin is what we call absolute zero. It's the coldest anything can be. And 0 Kelvin is roughly equivalent to 273 degrees Celsius. Technically, it's 273.15, pardon me, negative 273.15. But in your exams, you can use 273. So why bother remembering the 0.15? So 0 Kelvin, again, is absolute zero. It's the coldest anything can be. And that's equivalent to 200 or negative 273 degrees Celsius because it's super cold, right? Makes sense it's a negative number because 0 Kelvin is the coldest anything can be. That's why it's a negative Celsius, a really cold temperature. So let's say we've got a question here. It says we've got 2 kilograms of water at 25 degrees Celsius, cools to 0 degrees Celsius. Okay, so we want to, it freezes, I want to find the energy released. So again, I've got my 2 kilograms of water. So I've got my, let's say we've got just our water, we've got 2 kilograms, and we know that it's going to drop in temperature. So it's going to drop in temperature from 25 degrees Celsius down to 0 degrees Celsius. And we know anytime there's a change in temperature, we know to use the equation E equals MC, change in temperature, okay, because there's a change in temperature. So calculate that energy released because it's dropping in temperature. What we're going to do is our mass of our substance, which is 2, times the specific heat capacity, because it's water right now, we're using specific heat capacity of water, which is 4,200, times by the change in temperature. You might be thinking, you just said it has to be in Kelvin, but it doesn't matter if you convert both these numbers into Kelvin and then find the difference, or you just find the difference in temperature in degrees Celsius. Because it's a difference, it doesn't actually matter about the unit there. Whether you convert them both to Kelvin and then find the difference, or find the difference here, it still will always be a difference of 25, a drop of 25. Okay, again, if you look at your units for specific heat capacity, you can see our equation makes sense. You can see it's the energy required to change the temperature of 1 kilogram substance by 1 Kelvin. So that's where the units come from. So if I want to calculate that number then, all we're doing is 4,200 multiplied by 50, and we get an energy of 210,000 joules. So that's how much energy is released because of that drop in temperature. But it also it also tells us that it's going to freeze. Okay, we know freezing is a change in state. And from our earlier video there, we saw that anytime there's a change in state, we have to use this equation, that the energy from a change in state is equal to its mass times the specific latent heat of fusion. We use the specific latent heat of fusion because we're changing state from a liquid to a solid. So to calculate that energy released then, and we know there is going to be energy released because we're dropping the potential energy because we're making the particles get closer together. So that energy is the mass, again, is 2 kilograms. And that specific latent heat of fusion here is we're using is 3.4 times 10 to the power of 5. So when you multiply those numbers together, 3.4 times 10 to the power of 5 multiplied by 2 is going to give us 680,000 joules. So then the total energy now is just going to be, we add these two numbers together. So we're going to add on 210,000 to get a total energy of 890,000 joules, or you could say 890 kilojoules of energy is released. So remember, just always double check your numbers in your calculator because we can all make mistakes easily by just hitting a number wrong. 4,200 multiplied by the mass, multiplied by that change in temperature, and then we're adding on our mass times our 3.4 times 10 to the power 5 to get our 890 kilojoules of energy. The other way you might see it is what happens if we're dropping something inside water. So I would draw a picture to help you imagine it. So here what I have is my 10 grams of ice. First thing you're thinking, I'm a physics, can't be in grams. We know the unit is kilograms. So we're going to divide that number by 1,000. So we divide it by 10, you get 1, divided by 100 is 0.1. So 0.01 kilograms. So what we've got is our ice cube. My ice cube is a terrible drawing there. I got 0.01 kilograms of my ice cube. It's at -5 degrees Celsius. And we know that ice cube is dropped into water. So we could drop it into a bucket of water, and the bucket of water has got 0.1 kilograms of water. And we know that it's at 25 degrees Celsius. And we want to figure out what is that final equilibrium temperature reached. Okay, so we're trying to say it's in thermal equilibrium. Because we know when we drop the ice in there, that temperature is going to, temperature of the ice is going to increase, the temperature of the water is going to decrease until it becomes in thermal equilibrium. So we know the first thing that's going to happen is our ice has to first become a liquid water, right? So our ice has to change temperature from -5 degrees Celsius to 0 degrees Celsius, right? Because that's the temperature that we know ice is going to end up melting. Okay, and you have to remember this number, remember for ice or for liquid water. So the first energy we have there is our mass of our ice, which is 0.01, times the specific heat capacity of ice, which it told us here, is 2100, times that change in temperature. And again, because it's a change, it doesn't matter if you keep it in degrees Celsius or if you convert it both into Kelvin, because it's a change, that change is always going to be 5. Okay, so we can calculate the number out. We're going to do, again, we did 10 divided by 1,000 to get into kilograms, 0.01. We multiplied by 2,100, the specific heat capacity of ice. And we multiplied by 5, which is our change in temperature, to get 105 joules. Okay. Okay, now we know we have ice at 0 degrees Celsius that just became ice again. So what we did was we changed the temperature of ice from -5 to 0. So what we have now is ice at 0 degrees Celsius. But we know that ice at 0 degrees Celsius is now going to change state into a liquid at 0 degrees Celsius. And we know anytime there's a change in state, there's a change in energy. We know to use that equation, E equals m times L. So to calculate the energy of that change in state, we have to use our mass of our ice, because we have, again, we've got 0.01 kilograms of ice at 0 degrees Celsius. So 0.01 kilograms of ice at 0 degrees Celsius times the specific latent heat of fusion of ice, which we were told over here was 3.4 times 10 to the power 5. So we can find that energy to change state, which again is 0.01, multiplied by 3.4 times 10 to the power 5 to give us a number there of 3,400 joules. So that's the energy to change state from 0 degrees Celsius ice into 0 degrees liquid. So now we have liquid at 0 degrees Celsius. So I have a liquid at 0 degrees Celsius and I have a liquid at 25 degrees Celsius. So what's going to happen now is obviously those are going to come into thermal equilibrium with each other. So what's going to happen is my liquid at 0 degrees Celsius is going to start to increase in temperature. So we know to calculate that energy again for that increase in temperature is we're going to use our mass of our liquid at 0 degrees Celsius, which is 0.01, times the specific heat capacity of the liquid, because it's water. we're using the specific heat capacity of water, which is 4,200, times by its change in temperature, okay? So the change in temperature, normally we do is the final minus the initial, okay? It's going to increase in temperature. We don't know what that final temperature is, but the initial temperature is 0. So we're going to use degrees Celsius here. So we'll keep it 0. So anything take away 0 just becomes the same as that final temperature. So I can write here now is we're going to calculate what that final temperature is. So what I can do is 0.01 times by 4,200, which gives me that energy there is going to be 42 times by T. Okay, that's the energy it's going to be to increase our liquid water at 0 degrees Celsius to some final temperature. And the other thing we know what's happening here is that we have, again, our liquid at 25 degrees Celsius that is going to increase in temperature. Sorry. Our liquid at 25 degrees Celsius is going to decrease in temperature when we drop ice in it. So we know there's going to be a change in energy there. So I'm doing blue now for my water. Okay, so what we got here is we know that the energy is going to be the mass of our liquid, which was 0.1, times by the specific heat capacity of our liquid water, which again is 4,200, times by that change in temperature of our liquid water. And we normally, again, do our final minus our initial, okay? But we know it's going to drop in temperature. So that final number is going to be much smaller than our initial number. The initial number is 25 because it's dropping in temperature. Again, that final temperature is going to be lower than 25. So that's going to end up giving us a negative number. But when you do this equation, you have to have a magnitude in here. You can't have a negative number. So you can't write it as final minus 25. You actually have to write it as 25 minus whatever that final temperature is. So just remember here, and that's a key point to remember here, is that you always want to do the higher number minus the lower number inside that bracket. It's not always final minus initial. It's the higher number minus the lower number inside that bracket. And because it's dropping in temperature, the higher number is our 25. So what I can do now is I can factorize this out. So I'm going to do 0.1 times 4,200, which is 420. So I got 420 times 25. So I've got 10500, and then we're going to take away 420 T, just factorize out our brackets. So that's the energy of our water, and our water is dropping in temperature, so that's an energy drop. So hopefully now what we can see is that we had an energy drop of our water and we had an energy increase from our ice. So what we can do now is the energy drop from the water is going to equal the sum of all of our energy increases of our ice. So if we add all of those numbers together, so if we add our energy here for our ice to increase in temperature, which is 105, we're going to add it to the energy for our ice to change state, which is 3400, and we're going to get there 3505. So what I have now is 3505 plus my 42T for my ice, again, for my ice, my liquid, my ice that came liquid water to increase in temperature. Is going to equal the drop in temperature, so it's going to equal our 10500, take away our 420 T. So obviously now you want to bring all your numbers to one side and all your T's to one side. So what I'm going to do is add 420 T to both sides. So if I add 420 T to both sides, on this side, we're going to get 420 plus 42, which is 40, 50, 62. So 462 T is going to equal, so I added my 420 T to both sides. And what I do is take away my 3505 to both sides. So I'm going to do 10500, take away 3505 to get 6995. So calculate that final temperature, we divide both sides by 462. And we get a final temperature there of 15.1, and that's going to be in degrees Celsius, because in our brackets all the time, what we used was 0 degrees Celsius. Just make sure that you know your final temperature isn't in Kelvin, it's degrees Celsius, because we use 0 as the change in temperature state of water, 0 degrees Celsius. So just double check your math, because again, that's a lot typed in your calculator. So again, just looking at what we did here, we found the energy for our ice to increase in temperature, which was 0.01 times 2,100 times by 5 to find our energy for our ice to increase in temperature. We added it to the energy for our ice to change state, which is 0.01 times by 3.4 times 10 to the power 5. And then we added it to the change in temperature for our liquid ice to increase in temperature. So we added the 3505 to our 42T. We got 42T from doing 0.01 times by 4,200. Then we said that's going to equal to the drop in temperature of our water, which was our mass of our water, which was 0.1 times 4,200, the specific heat capacity of water, times by 25 to give us 10500. And then we had multiplied by negative T, so 420T. So we equal to those now. So what I had now is I took this number away from both sides. So I subtracted 3505 from both sides to get 6995. And I added my 420 to each side. We did 42 plus our 420 to get 462T. To get T then, we did 6995 divided by 462. And we got a final answer of 15.1 degrees Celsius, which makes sense because our water at 25 dropped to 15.1 degrees Celsius, and our ice changed state to water at 0 degrees Celsius that increased in temperature to 15.1 degrees Celsius. So, grand. Hopefully you find that helpful.